Hello class. So on this video, we'll continue on section 3.7. We started example 2 in the previous video. As we had this set up, let me read it again. A mass weighing 2 pounds stretches a spring 6 inches. At t equals 0, the mass is released from a point 8 inches below the equilibrium position with an upward velocity of 4/3 feet per second. Now, we want to determine the equation of motion, right? So this corresponds to undamped, right? So there's no dampness, free vibration, simple harmonic motion. So we know the differential equation. To solve that, we just need to find the things that we wrote last time. We need to find what K is, we need to find what M is, and we need to make sure that all of the units match, right? Now, I gave the units like this all messed up because I want to give you a little bit of an example of how you have to be careful of what the units are. Okay? So I wrote a couple things here. What I want to do is I want to work with everything in meters, right? So that's one thing. I want to change all the feet to meters, and I also want to change pounds to newtons. Okay? And so here in the box on the bottom right, I did that, right? So it's an approximation. I'm always going to be rounded in this back to 3 decimal places, right? So 8 inches is approximately 0.203 meters. Right? Now 4/3 feet per second, right? I want to convert to meters per second, right, for velocity. How am I going to do that? Well, I'm going to show you a trick that if you've done chemistry or physics, you already know how to do this. But the idea is you can multiply 4/3 feet per second times 1, right? So we're not changing anything, but in a very clever way. Right? So the idea is write 4/3, right, feet per second, and I multiply this by 1. How am I going to multiply this by 1? Well, I know that 1 meter equals it's approximately 3.281 feet. Right? So again, I'm always only rounding to 3 decimal places. So what I want to do is I want the feet to cancel, and I want to have meters. So I'm going to multiply this by 1 like this. Okay. 1 meter is, again, approximately 3.281 feet. So I'm going to write 3.281 feet here, okay, and I'm going to write 1 meter here. Now, notice, by definition, 1 meter over 3.281 feet is approximately 1. So think of this just multiplying by 1. We're not changing anything, right? But the units cancel where we want them to cancel, and we're left with 4/3 times 1 over 3.281 meters per second. And that, let me simplify in my calculator to 3 decimal places, so it's an easier number to work with. So 4/3 divided by 3.281. This is 0.406 meters per second. And it's approximately, but I already wrote the approximate sign before, so I'm just gonna, so it's a second approximation, but still, I already have an approximation before. But no, it's a different one. It's a different approximation. So I need to use, it's approximately 0.406 meters per second. Right. So that's how you do dimension analysis, right? So, or not, it's a subset of dimension analysis, but that's how you change units. Right? You multiply by 1 in a nice way so that the units cancel. Right. Now, I also wanted to change my 2 pounds to newtons. Right? Newtons is kilograms times meters per second squared. Right. Pounds, I don't know exactly what the unit for that is. That's why I want to change to newtons. Right. But pounds is a force. Right. It's weight. Right. So weight we know is a force. Right? So I just change it to newtons. Right. So 2 pounds is approximately 8.896 newtons, right, which is 8.896 kilograms times meters per second squared. Okay, so now let me write the initial conditions first in terms of these new values. So again, 8 inches is 0.203 meters. 4/3 feet per second is 0.406 meters per second. Okay. Now, let's find K. How do we find K? Well, we find K basically doing the same thing I mentioned here, and it's fine if you can remember, but using the fact that at equilibrium, right? So when the weight, after the weight stretches the spring, right, it reaches an equilibrium state. That equilibrium state is exactly when the magnitude of the restoration force is equal to the magnitude of the weight. So we can use that here. So that's example 3, sorry. Let's go back to example 2. Right, so let's do the calculation. So we're given that a mass weighing 2 pounds stretches the spring 6 inches, right? And we know 6, okay, so we have to convert 6 inches to meters as well. Because again, I want to work only with meters. So let's do that conversion. 6 inches is approximately, let me just do this one on my computer or my calculator. So 6 inches to meters. So approximately 0.152 meters. Okay. So we know that this restoration force has to be proportional, right, to how much the string was stretched. Okay. The string was stretched 0.152 meters, so it has to be K times 0.152, where K is a proportionality constant. And I'm going to drop the units for now, because we already know the units are correct. Now, at this point, we know that we're at equilibrium, right? After the weight stretches the spring 6 inches, or 0.152 meters, we're at equilibrium. So we know that the magnitude of this force is equal to the magnitude of the weight. The weight is given by 8.896 newtons. Right? That we know that's the weight. That's a mass weighing 2 pounds. Pounds in newtons is 8.896. So what do? We set them equal to each other. So the weight at equilibrium has to be equal to this force here, to this restoration force. In magnitude, right? So anytime anything's negative, you just take the absolute value. Okay? And this is, again, how I mentioned in the previous video, how you can know, not based on us giving K a specific sign, but just from the setup that K is always going to be positive. Right? K is going to be 8.896 divided by 0.152. And I'm going to write that as 3 decimal places. So approximately 8.896 divided by 0.152. So 58.526. Now, notice that I don't write units for K, because the units don't really matter for this constant. You could find the meters, right, just by dividing by all the, for example, 0.152 is in meters, 8.896 is in newtons. So when you divide, what do you get? You get newtons per meter. Or kilograms, because the meters cancel, kilograms per second squared. Right? But again, the unit for K is not that important, because all of the units before are already set. And remember, for K, we're really just interested in the number. So as long as all the units you use to find K are correct, then you're good. You don't need to worry about the units for K. Right? So now we did the first one. We found K. Now, how do we find the mass? Okay, so let me do a division here. How do we find the mass? Well, we're given the weight. We should be able to find the mass if we know the weight, because we also know the acceleration due to gravity. Okay. So we know that the weight is equal to 8.896 newtons. Remember, weight is acceleration due to gravity times mass. Right? So this is equal to acceleration due to gravity, which is 9.8 meters per second squared. And notice why it was important for me to work with meters in seconds, because I'm using an acceleration in terms of meters in seconds. Right? So I want to make sure that all the units that I'm using above are in meters. So basically, the fact that I'm using 9.8 for my acceleration due to gravity forces me to use meters for all of the other distances and seconds for all of the other times. Now, again, you can choose any units that you want as long as all of the units match in your calculations. If not, your units are going to be all way off. So we know this is this times, so I'm using M for meters. So let me use kilograms for mass. That's what I'm using, kilograms. So times some kilograms. So let's say X kilograms. Right, where X is going to be the mass that we're looking for. Okay, so let's solve for X. Right, so divide both sides. So we get 8.896 newtons divided by 9.8 meters per second squared. And this is going to be equal to X kilograms, which we're going to approximate. Again, I don't want to write it with more than 3 decimal places. So 8.896 divided by 9.8, I get 87.181. And you can know that the units are correct. You know this is kilograms because newtons is kilograms per meters per second squared. Divide by meters per second squared, and you're only left with kilograms. Right? So you know that the units match. And that's our mass. Right? So let's go ahead and fill it up here at the start. So K, again, the units for K don't really matter. You can find them if you want, but they don't really matter. The same for M, they don't really matter, but it was important for us to use the right units as we were finding M. Right, so K here is going to be, where was it? Where was K? 58.526, approximately. Now, all of these numbers are actually rational, meaning that I could have written them exactly. I just don't want to use more than 3 decimals. So it's really just me trying to simplify what I'm writing by not using too many decimal places, but everything is rational. So you could have just written everything exactly, so we really don't lose any information when we convert to units, other units, as long as we don't approximate. I did, so I am losing a little bit. I am just doing an approximation, but it's going to be close enough. I mean, 3 decimal places is pretty close to, it's pretty good. Then mass was 87.181. Let me write kilograms here. 87.981. And now we're done with this part. This is the hard part, like making sure that all the units are good. Actually solving the differential equation, it's easy. We've done it a bunch of times. So let's go ahead. We have x double prime plus w squared x equals 0, right? Where w is the square root of k over m. So in our case, this is the square root of, so on the bottom is 87.181. 87.181. On the top, we have 58.526. And this, I'm going to leave it like that, right? So it's actually exciting. I don't want to approximate anymore for now. But this is some number, right? Okay. Now, that's all we need, right? You can go through all the work, but we already did that when we found the general solution. All we really needed to know was find W. So let me do it in another color. So it implies. So the general solution, and it's a homogeneous differential equation, so I'll write as y sub c equals c1 times cosine of w, right? Which is the square root of that number, so 58.526 over 87.181 t, right? Plus c2 times sine of that. The square root should be on everything. Okay. But we also have initial conditions. So let's use them to solve for C1 and C2. You know that x of 0 has to be equal to 2.203. That's the first condition. So let's use that. So x of 0 equals C1, cosine of 0 times anything is 0, plus C2, sine of 0 times anything is 0. This should be equal to 0.203. So cosine of 0 is 1, so C1 plus sine of 0 is 0. So it's plus 0 equals 0.203. So we found our C1. Now let's find the derivative, because the second initial condition is a velocity condition, right? So we need to find the derivative. So we have, so x prime, let's first find this. It's going to be, so C1 is 0.203. So it's going to be negative 0.203 times omega, W. Remember, W is the square root of 58.526 divided by 87.181. So just so I don't write that a bunch of times, it's going to write W, sine of WT plus C2. Oh, no, sorry, the derivative. Yeah, okay, derivative. So C2 is cosine. We bring the whatever's inside outside. So W cosine of WT. The initial condition is x prime of 0 is, where is it? 0.406, right? So x prime of 0 equals negative 0.203 W sine of 0, right? Anything, W times 0 is 0, anything times 0 is 0, plus C2, W times cosine, again, anything times 0 is 0. We know that sine of 0 is just 0, so it just becomes C2. Cosine of 0 is W, so C2 times W. And this has to be equal to 0.4, what? What was it? 0.406. Solve for C2. So what's the general solution? Well, it says C1, which was 0.203, cosine of W, which we know what it is. I'm just writing it as W for now, plus, assuming I did all the algebra right, you can check while you go over the video, sine of WT. That's the answer. So as you see, finding the solution is pretty easy because we know how to solve a differential equation like this. What's hard is actually doing all this unit conversion. But again, I do it because I wanted to see how to do it. Units matter. When you're calculating things, you want to make sure that your units match so you don't get any mismatching units and everything cancels out nicely. And I do it for me as well because I'm used to working with kilograms, meters, seconds, right? So I don't usually work with feet, inches, or pounds, right? So I also work with newtons. So I guess I'm just more comfortable working with things like this. And again, all of this could have been done exactly. I was just approximating to 3 decimal places. Now, if I don't ask you to change units, so I might just give you a problem where all the units match, you don't have to change anything if you don't want to. Right? But again, substance, you're forced. Because if you don't want to change units of what you're given, then maybe you have to change the units of the acceleration due to gravity. Like if you're working with feet per days, right, and you want to change that, then you're probably going to have to change the acceleration due to gravity from meters per second squared to, what would it be? What did I just say? Feet per day squared, right? So something you might have to do. And that's the answer, right? Again, it's not obvious that this is a solution that's just one sine, right, or one cosine. Right? But I'm going to show you the formula to get that in the next section, in the next video.